Yeah. All right. Yeah, we can start now.
Okay. Can I also turn off my camera?
Yeah,
Yep.
sure.
Okay. Thank you. Uh, hello everyone. Let me share. Put this here. Sorry, I'm dealing with technology. Hey, everyone can see my screen, right? Yes.
Yes.
Okay. Okay, so today we would be having a conversation about distributed transactions. But I figured the title should say distributed systems because who am I? My name is Chidinma Kalu. I am a software engineer at booking.com here in Amsterdam. That's my website, and you can find me on Twitter at ChidinmaKO. Today we'll be discussing what transactions mean. We'll talk about asset properties. We'll talk about distributed transactions, two-phase commits, three-phase commits, database partitioning, halving, spanner, and percolator. Yeah. Because this is a conversation, if you have any questions, feel free to interrupt me, raise up your hand, and yeah, we can delve. We can delve more into whatever thing you want to talk about. So yeah, what exactly is a transaction? Transaction is basically a set of operations executed as a single indivisible unit of work on a database, ensuring the asset properties. This means that a transaction is a way for an application to group several reads and write together into logical units. Basically, the transaction can either succeed or fail. Yeah, so if the entire transaction fails, it can be retried without having to worry about partial failures. So basically, now we're going to recap what ACID means, just in case some of us have forgotten or we just need a refresher. So when I read this, I said just as an atom cannot be split without changing its essential nature, I had to go research, can an atom now be split? And apparently it can. So that's me digressing. Atomicity is basically a guarantee that either all of the operations in the transaction are completed or none of them take effect. Right, this is very important because you would not want, yeah, at the time of writing. Yeah, so basically, with atomicity or with transactions, you would not want, say you want to credit debits from one account and credit it to another, you would not want one part to go to succeed and the other to not, right? That's why atomicity is quite important. And basically, transactions should be recoverable. So in case of an unsuccessful transaction execution, database can be reverted to its previous state. Consistency guarantees that a transaction transitions the database from a valid state to another rather, while maintaining the database's predefined rules. I don't know if this is something we've come across, but consistency, we have ACID, but consistency is really the only guarantee that falls on the application, not really the database. I mean, the database and the application work together to guarantee consistency, but it falls more on the application. I just wanted to mention that. Yeah, so isolation ensures, oh yeah, yes.
What do you mean? Why does it fall on the application?
Okay. Let me try to explain that. Yes. So, like I said, it falls more on the application and just the not just the database. Database can actually just enforce constraints like and triggers like, hey, foreign keys, unique constraints, but really it's up to the application to define and uphold the validity of the data, right? So it's the application that defines the constraint like account balances cannot be negative, inventory levels cannot be below zero. So basically, we can say that while the database provides mechanisms to maintain atomicity, isolation, durability, both the database and the application share the responsibility for maintaining consistency. Does that make any sense to you?
I think so. Yes, it does. Okay. I feel like it's more maybe shared responsibility versus just application because
No, I did not say just the application. I said both the application and database share the responsibility,
okay.
right? But most of these predefined rules are specific to the application because they are the ones that define what a valid state is.
Yeah. I mean, but you can also like specify what the valid state is in your schema. You can also like specify it in like I forget what these things are called, but you can add these checks to your
Database.
I can't remember what they're called, but yeah, like but anyway, yeah, I understand. Thank you.
Yeah. Triggers, yeah, I said that earlier. I said the database can enforce the constraints and triggers, for instance, like foreign keys and unique constraints. But really, I I believe that the application. That's what I'm going to ask you is earlier. Is that a question? Yes, good to go.
So I think defining it like that's saying it falls mainly on the application. Um, if you looking at it like that, it's sort of a different perspective. I can say that if you, for example, if you have an application, you can define the schema. You can say maybe for an address column, only strings should be entered there. But you can't really say from the database doesn't really know if it's an actual address. So meaning if you actually enter the person's name from the application and the database can't enforce that. It can only enforce that it's a string. So I think that's what they mean when they say the consistency depends um, more on the application than the database. I think that's the definition. Even though the database enforces consistency in its own way and other sites, there is also a dependency on the application to enforce the consistency. I think that's what they mean by that.
Yes, I think that explains what I was trying to say. Yeah, thank you. Okay. Durability guarantees that once a transaction has been committed, its changes are permanently recorded in the database, even in the event of system failures. This means that the changes made by the transaction are saved to a non-volatile storage. So now we are at distributed transactions. So unlike just a transaction that happens in one database, distributed transaction involves like multiple databases. And this makes it a bit hard to achieve ACID guarantees because like it would require coordination across all participants, right? You want all the participants to like commit or roll back as if it's a single atomic operation. Now, what is atomic commitment? In a database that supports transactions across multiple nodes or partitions, we face the challenge that the transaction might fail on some nodes but succeed on others. I had to research because I kept saying atomic commit and atomic commitment. And I had to put it down that the challenge of making all of this multiple nodes or partitions act like a single atomic transaction or achieve atomic commitment. That's actually the challenge. However, we use atomic commitment algorithms to ensure that a distributed transaction like either fully commits on all nodes or fully aborts on all nodes. Yeah, so basically atomic commitment guarantees consistency even in the presence of failures. Yes, Damila.
Hi. So one thing I found confusing was what we are trying to like the transactions, distributed transactions.
Yeah.
What nodes are we trying to accomplish this on? Because we've talked about replicas in the past,
Yeah.
and to me, if we carry out a transaction on one node and then it's replicated across other replicas, I don't see why we would need some distributed transactions, since replicas probably just read like the write ahead log and replicate whatever has gone on in the write ahead log of maybe some master node across like the replicas. So I was trying to understand, like, is this distributed transaction, is it across nodes with different set of data like shards or partitions, or nodes that are replicas but we still want to achieve distributed transaction across them?
Like, oh,
Yeah.
yeah, I am ready.
So something that's so there is a database at Google called Colossus. I feel like Colossus is public app. I'm not supposing anything. Anyway, there's a database called Colossus that is. Sorry, let me do a check real quick. Give me a second. Just want to make sure that. Okay, yeah. So the database is called Colossus. And you can define different levels of, what would I call them now? I can't remember what the technical term is, but if you want to write to a Colossus like set, like the Colossus database, it wouldn't, depending on how you tune it, it wouldn't return successful to you until it has written to 2 or more. Like, depends on what threshold you set, right? But it wouldn't return a success status to you until it has written to like multiple nodes. And like this guarantee is very important for like file systems, for databases. So I kind of imagine it that way. So sometimes it's fine, like depending on the requirements, it's fine to write to like a leader, node, and the leader would write to others. But in some other systems like Colossus, they allow you like force writing to 2 separate nodes before returning success.
So it sounds like in this case, instead of having one primary write node, we would have multiple write nodes carrying out the same operation. So if I'm writing,
No, I mean, you don't think about it like, it kind of depends on what, like, you can have write nodes that write to 2 separate locations, right? Like you can have one write node write to 2 separate locations. So it kind of depends on what we mean here by like, so a node here can be like the storage cells. The node itself can be the nodes that you send the write request to, right? I can send a write request to one node, but that write request will not return successfully to me until it has written to 2 separate storage locations. So that if, I don't know, something happens to one, like we're sure is another one, like an M+2 type thing. So yeah.
Okay, I'm just trying to understand the context of why we would need distributed transactions. Yeah, okay.
So I think I can like think of 2 separate scenarios, one on a replica database and another one on a partitioned one where you would need this. So for example, if you had like a a set of nodes which are replicas, let's say 2 or 3 of them, and then your application is maybe an application that manages the hospital record, and of course a doctor has to be on call and every time. So if a doctor wants to leave, he would have to um, drop leave sort of from the software or whatever. But for that to happen successfully, he has to make sure that there is a doctor available. So imagine 2 doctors trying to leave at almost the same time, maybe due to an emergency or whatever. And then you make a read request to a replica, uh, and the other doctor makes another read request. But if both of them have already left, maybe for one replica, it says that the doctor is already done. So that propagates to the other replicas. You need to be sure that from the other replica. Sorry, I mixed up my thoughts here and it's getting a bit confusing. So I'm just going to start from the beginning. So if you if you have let's say 3 nodes, for example, and then the doctors want to each leave, and they would have to send a request saying that they would want to leave, and maybe to the database, and the database has to check if there is a doctor on call, and then if there is no doctor on call, it says, sorry, you can't leave now, you have to wait for a doctor to come in. So imagine 2 people making that request at the same time. Now, if all the replicas don't have exactly the same data, right? We discussed quorums and a couple of other things which could ensure that that doesn't happen. But if all the replicas don't have exactly the same data, one could say that the other doctor is still available since they're making the request at relatively the same time. And technically, the other one could also say that the doctor who has already left is also available. I don't know if that makes sense, but if they are sort of making the request at the same time and 2 replicas have like the same information or different information at relatively the same time, that could cause like a conflict. So both of them would technically be able to leave, seeing that the other one is available on one replica, and on the other replica, one is available and the other isn't. I don't know if that makes sense, or I should think of like a better example.
I mean, I think it does, right? I feel like in systems where we want to force like hard consistency, and for example, we need multiple. So if I think on like server level, or in fact any level, database, servers, whatever, we need multiple shards to serve multiple people or multiple requests. And we want to force consistency so that when, for example, so let me like think of like a database where, or like a system where like someone, or like every node, just for some reason, every node kind of serves requests to different people. And it is very important that the data on all of these nodes are always accurate. If a request is written to just one of those nodes, and we're banking on the replication happening asynchronously, it's possible that it fails, or something slows it down, or it could just not get delivered for different reasons. And some other like request is made from another node that hasn't been written to yet, that gets inaccurate data. Like there are a lot of scenarios where like that could be catastrophic, like depending on what the context is. So that is one context where like you want to force like hard consistency because of the requirement reasons. In the case of databases, for example, there are also requirements that you like guarantees you need. So a lot of like cloud systems offer like database solutions where they tell you n+2, right? Like right, yeah. Sorry, where they tell you n+2 is a guarantee. So if like a location is down, or a node fails in a location, in another location, we should still be fine. The only way to really guarantee that, you can decide to do this asynchronously, and maybe it would work, for most situations. Maybe it would work even like, so I can think of a scenario where like you write to the data, to your node, to the one node, it returns success to you. Then you write to another node, the replica node, it is successful. And then the primary node fails. So the replica node already has this information. But there's a scenario where the replica node fails. The replica node doesn't get this information before the primary fails. And so the guarantee is gone. So the way you would force this guarantee to be true, especially like where legal, like you've made like legal commitments. The way you would force it to be true is by ensuring that before you return like a success, the write is done. So it can kind of be like a mix, right? So if you have like six nodes in your cluster, right, like you want to replicate all the data to, and you want to ensure it's written to 2 first before you return a success, then 2 nodes need to be written to synchronously, and then you can write asynchronously to others. This doesn't mean that 2 of them are primary. This doesn't really imply anything to us. It just tells us that you're forcing your application to write to 2 nodes, like because of some requirements. One of them could be primary, 2 of them could be primary. I don't know. That kind of just depends on how the system is set up. But yeah.
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 Okay. So another thing I had to understand to sort of figure this out and understand why it's important for both the replicas and the partition databases is the fact that a transaction is actually a list of actions that would happen, not just one. So, for example, a transaction could be to make a transfer from one account to another. So, but for you to debit this account, you have to make sure the money is credited on the other account. So you need to perform a read before you perform the write, and you need to make sure that the 2 of them happen atomically. So you need to make sure that the 2 of them happen as if it was one action, as if they were immediate. So it wouldn't happen that another transaction, which is running concurrently, maybe trying to also debit the same account, or credit the same accounts, maybe credits once, twice, something like that. So the fact that a transaction is not actually just one action, is actually a set of instructions that need to happen, and they need to happen as if it's one action. So I think that helped me understand.
Thank you, good Chuku. But like Chuku credit. What comes to my head when I think about replication and distributed transaction is like replication is primarily about data redundancy and availability, just like everyone has said. You want your data to be available on like multiple servers or in different locations, in case one fails, then the other will take over. And distributed transactions, like is basically about ensuring consistency across multiple systems, right? Yeah. So if you're trying to credit one account and debit the other, say for instance you credit the account and the debit fails because it doesn't happen at the same time, right? And then it's replicated to other databases, the data integrity is compromised, right? So that's why we need both replication and distributed transactions. I don't know if like all of our input has convinced you and not confused you. Damilola.
As the n+2 example made it perfect. So if we want to make sure that every write is there's some redundancy there. So if we just approach it from the primary and read replicas, if the primary is down, then writes might probably be down. I mean, although in that one you can have another read replica replace the primary, but yeah, if you want to go with the n+2 approach, then this makes sense. Yeah, I think.
Sorry, but I was kind of hoping that someone would just mention like the simple case of, you have like 3 servers and each of those servers have their own separate databases with different data. And then like you have like application logic that depends on data that's in all those 3 databases, right? So you need like a transaction that's wrapping all those separate data stores. I hope that makes sense. Like, because that's like the traditional like two-phase commit, like problem. Oops. Sorry, never mind. Just, go ahead.
Thank you. So where are we? Okay, I think we haven't talked about this. Yeah, so atomic commitment's main purpose is to solve the problem of reaching an agreement on whether or not to execute the proposed transaction. Many distributed systems use atomic commitment algorithms like MySQL for distributed transactions and Kafka for producer-consumer interaction. Many people confuse atomic commits and consensus. I fear that this is the part where we're going to have more conversations. So yeah, atomic commit ensures that a series of operations either all succeed or all fail to maintain system consistency. And consensus, in my opinion, is a broader concept where multiple nodes in a distributed system agree on a single value, data value or state, also ensuring consistency across the system. I made a table. So basically, we talked about the purpose of both atomic commit and consensus. The process for atomic commit is every node must vote whether to commit or abort. However, in consensus, I think we'll talk about consensus next week. But yeah, one or more nodes propose a value. The outcome in atomic commit is that the transaction must commit if all the nodes vote to commit and must abort if all nodes vote to abort. In consensus, any of the proposed values is chosen. Failure handling in atomic commits. If a participating node crashes, the transaction must abort. However, in consensus, algorithms like Raft can tolerate crashes as long as there is a quorum of nodes, as long as a quorum of nodes is working. Yeah. Protocols in atomic commit is two-phase commit and three-phase commits. I mean, those are commonly talked about protocols to achieve atomic commitments. Consensus algorithms that are commonly talked about, Paxos and Raft. The focus of atomic commit is transaction integrity and consistency in distributed systems. However, consensus focuses on maintaining a consistent state and fault tolerance in distributed systems. Any questions? No? Okay. So now we'll talk about two-phase commit. Like I said earlier, two-phase commit is a common protocol used in distributed systems to ensure that all participating. Oh, sorry. Any questions? Going once? Going two?
No, I don't. I don't know. Is consensus versus atomic commitments confusing to anyone?
Yes, because when I was I watched Martin Klepman's distributed transaction series, or distributed system series rather, and I was discussing with a friend, and she kept saying like this seemed like, because we will talk about atomic commit protocols that actually use Raft and use Paxos, right? And she kept saying she doesn't see the difference. Like both of them seem to like have to vote, have to like choose something, have to reach an agreement. So it seemed like they're both confusing. And I figured there are people who might find it confusing out there. So that's why I added it. But apparently we are all experts, so.
No, not really. I'm just I think maybe like the lines will blur as we go into the details, but
yes,
on a high level, it kind of, especially if I think about this like in relation to like requests, like I think about requests being made to like a server or like a database node, and we're trying to like enforce commitments, like atomic commitments in that light. Like when I think of consensus, that's not what I'm thinking about. I'm not sure. Like anyway, yeah, we'll see as we go.
okay. Yes. Two-phase commits. Two-phase commits involves a leader, commonly known as the coordinator, and the participants, also known as the cohorts. In the database internals book, which we are currently talking about, cohorts is used repeatedly, but like in my presentation, sometimes I think I say participants a lot more. So yeah, the coordinator holds the state, it collects the votes, and is the primary point of reference for the agreement round. 2PC has two phases, the prepare phase and the commit phase. Somebody mentioned write-ahead logs earlier, and I'm grateful that I did this here. So basically, two-phase commit uses logs, write-ahead logs, to ensure that decisions taken related to the transaction are recorded before any actual commit or abort actions are taken. I'm sorry. These logs are typically stored in stable storage to survive crashes and reboots. And we should also try to remember that every log entry usually contains the transaction ID, the state, and possibly other metadata such as timestamps. The coordinator log ensures that in event of a failure, the coordinator can recover the transaction based on the persistent decisions rather. The participant log helps each participant recover from failures and resume its part in the distributed transaction processing. The participant log also contains the participant's decision to commit or abort, and also the coordinator's final decision. So yeah, back to the phases. The prepare phase is the first step. During this phase, the coordinator sends a prepare request to all the participating nodes, asking them, hey, can you commit this new transaction? Right? And basically what happens is locally, every single participating node does the necessary checks. They kind of do it locally, but they do not commit yet, right? And if everything is fine on their end, they vote with yes if they can commit, if everything is fine, or no if they cannot. Yeah, and this is because remember I said earlier that the transaction details and some other metadata are sent to the participants. Like I said earlier, each participant executes the transaction locally, blah, 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 blah. It can commit without conflict before it can vote. Yeah, after the local execution of the transaction enters a partially committed state where the changes made by the transaction are recorded. The transaction is ready to be finalized, but isn't fully committed, and the changes can either be committed or rolled back based on the final decision. This leads us to the commit phase. Now, if all the participants has said yes, the coordinator sends a commit request to all the participants, and if any of the participants voted no, the coordinator sends an abort request instead. And yeah, all the nodes can then commit or abort based on the coordinator's final decision. And I have a lovely diagram. I think this is the end of 2PC. So give us a minute to look at the diagram, and if you have any questions or you have, yes.
So the genuine question here, right? This is something that has always kind of confused me about two-phase, right? Because we know in a distributed system, there's like the network is unreliable and blah blah blah. You need to send messages and stuff, right? So if two-phase is relying on it's sending a message and it's proposing, say, okay, everybody, let's try to prepare to commit this transaction, doesn't it fall back to this? I need to wait for an acknowledgement that all the other nodes receives that commit or abort. I don't know if that makes sense.
Yeah, so I think you're talking about the blocking issue that 2PC faces.
No, not blocking, right?
Okay.
what's confusing me is that doesn't it need like n+1 acknowledgements, right? Because you say, okay, let's all try to commit, and then like what if like one of the nodes never reaches back, like things like that.
So
Yeah.
you're asking if one of the nodes doesn't respond during the propose or the commit phase, right?
Yes. So will it like completely abort the entire transaction and then like try to propose the transaction again and things like that?
Yes, I think yes, it's actually going to abort. So in the propose phase, if it says, can you commit this transaction? Is this something you're willing to do? And one of them doesn't respond, it is definitely going to fail. Yeah, but Ugochukwu has something to add, I think.
Yeah, you're right, Haley. That's a concern for 2PC. But towards the end of the chapter and like later on, the author mentioned Paxos groups, which is Paxos is a form of consensus. So they sort of find other ways to like make that decision without having to without all the nodes having to confirm that the the transaction can be done, right? So they make Paxos groups, which is basically grouping nodes based on a particular reason, maybe because they are in the same location or they contain the same data, or just there's a reason, and then they group the nodes and then they can have a leader. So the Paxos leader would be the one who does the reply to the coordinator that okay, we can commit this message, or we can commit this transaction rather without having any issues. So that way just the leader would be the one who does the messaging. And then also, if there is a network partition on the side of the leader, the members of that Paxos group rather, could re-elect a new leader using the algorithms we've talked about before. So, and then there are a lot of other things, if you like do more research, a lot of other ways where they try to reduce the number of nodes, maybe use quorums or something like that. They try to reduce that because it's a problem. But it's still widely used because the other one, which we should talk about, 3PC, has a higher message overhead. So there's still a lot of more messages that will be sent by 3PC. So it's better to optimize 2PC, which they do in those ways.
Yes, Ugochukwu, were you referring to spanner?
Yes, spanner,
Okay.
I think.
Okay, because I read that there is actually a way to make 2PC fault tolerance, like more fault tolerance, and there is something called Paxos-based fault tolerance 2PC. I did not cover it in this presentation because I felt it was out of the scope of the book. But yeah, using Paxos, but not in the spanner way, right? Basically, you just use Paxos to make sure that all the nodes does not need to be available to vote, right? So if a quorum says, yeah, it's fine, we can commit this, then yeah, it will be committed. But that's also a way to make your 2PC more fault tolerant. Yeah.
Sorry, I don't know that that was my question. I wasn't actually asking about fault tolerance. It was more so that at least to me, it seems like maybe never mind. Like I'll ask in the Discord.
So I think that Heidi, the like 2PC, that's kind of the constraint in it, as far as I understand anyway, right? Like all the nodes either agree or they don't. The other like algorithms, I think, begin to now talk about how do you get maybe majority of nodes to agree, and maybe if majority agree, then we commit. If majority don't agree, then we don't commit, right? So, but there will need to be some, like, if nodes are failing, there needs to be some threshold, I think. Like, I don't know, different methods will need to define what the threshold for committing or aborting is. And I think 2PC is just everything either agrees or not.
Yeah, right? But like the question is more that, how do you know that you only need like a propose and commit phase, right? Because what if like, like the classic like n plus, like you need an acknowledgement that the nodes received the propose and then the commit and like so on and so forth. So why would like a two-phase be even better than or why would a three-phase be better than a two-phase? Like why not like a 1,000-phase? To like be like, if that makes sense.
Okay, let's
Sounds
continue.
like a visiting general's issue, right? Like
Yeah, exactly.
you're going round and round, like chicken
Yeah,
and egg. Okay.
like how does the two-phase commit avoid that problem? Like it's not clear to me that like even when like you have like if the two-phase commit goes through like successfully, right? Like you propose, they vote, and then they commit. Like how do you know that, well, they committed, right? Like
Yeah. So if we look
Sorry,
at the
they
last
send
step, let's say, oh, sorry. Let me just, if we look at the last step, it's an acknowledgement that they committed, right? So if I think this is a question that might answer your question. Like, so if the acknowledgement fails for a particular cohort, I think that's what they are called, does the coordinator assume that the transaction failed? Like it's not over?
exactly.
Yeah,
Yes.
I think that would answer the question. If it doesn't care about the commitment acknowledgement, then maybe. But how would they know that every? Yeah, I get you. Yeah.
I think if I understand the question, because maybe I don't really understand well. Aside to that acknowledgement, right? He also mentioned if a member, or sorry, cohort drops, maybe due to network issues, or maybe it just stops working when it comes back online, based on the algorithm set up in the database management system, it can either ask the coordinator for its own logs. So the coordinator assumes that they have all committed after it sends the commit message. Once it receives the once it sends the commit message, it assumes everybody can commit and should commit if everything works fine. But if everything doesn't work fine, once the one who wasn't able to send the commit acknowledgement comes back online, guessing the coordinator would probably need to send its own log, or it can also request the logs from other people and ensure it's on track. So that was all he said about it. He didn't go into more details about it.
Heidi, I think you should let's talk about this on the thing.
Yeah.
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 Thanks everyone. Yeah.
Thank you. Yeah, I mentioned I wrote about the problems with 2PC blocking. So basically, if the coordinator fails after sending a prepare message, but before sending a commit or abort decision, the participants basically remain in a blocked state and would not be able to make progress. Right? This is one of the major problems with 2PC. There's also the single point of failure where the coordinator is basically like if it goes down, then the entire transaction will be stuck, right? Until another new coordinator takes over or that particular coordinator recovers. 2PC requires multiple rounds. I mean, not as much as 3PC, which we will discuss like in the next few slides, but still requires multiple rounds. Like, are you ready to commit? Is this fine with you? Then vote yes, blah, 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 blah. There's also resource locking, right? During the prepare phase, participants have to lock resources to ensure that they can commit if asked. And this can lead to like a higher contention footprint and performance bottlenecks. Network partition too. Yeah, so in the case of network partitions, where some participants become unreachable, 2PC can lead to indefinite blocking. Yeah, I think these are some of the problems with 2PC, but now we're in 3PC. 3PC basically like addresses some of the issues of 2PC, but also comes with its downsides. One of the problems that 3PC solves is the blocking problem. 3PC introduces like an additional step and also incorporates timeouts. Basically, these timeouts enable participants to proceed with either committing or aborting the transaction in the event of a coordinator failure based on the current system state. 3PC has 3 phases: propose, prepare, and commit. The propose phase is also known as the can commit phase. I think many literature also specifically use can commit phase instead of propose phase. The coordinator sends out the proposed transaction value along with the can commit message to all the participants asking if they can commit the transaction. The participants evaluate the proposed value, just like I talked about in 2PC, and then they vote yes or no, but they do not commit yet. In this layer, if the coordinator fails during this phase and the operation times out, or if one of the cohorts votes negatively, then the transaction will be aborted. The prepare phase is also known as the pre-commit phase. Basically here, if all the participants agree to commit, the coordinator sends a pre-commit message instructing them to prepare for the final commit. Then the participant has to acknowledge receipt of the pre-commit message by sending an acknowledge, back to the coordinator. However, if any participant votes no during this phase, the coordinator has to send an abort message and the transaction is aborted. This phase, this prepare phase or pre-commit phase, only proceeds if all the participants agree to commit, right? And in this phase, once the participants have received the pre-commit message and sent the acknowledgement, if any failure happens on both sides, the transaction will be committed regardless. And now we are the last phase of 3PC, and this is called the commit phase, also known as the do commit phase. After receiving acknowledgements from all the participants, the coordinator sends a do commit message to finalize the transaction. In this phase, the coordinator also resets the timeout counters of the participants. And the participants, after executing the transaction, sends a final acknowledgement indicating that the transaction has been committed or completed. And this is a nice diagram from the book. Any questions? No? No? Okay. Now let's look at some of the problems. You can ask. Okay. That was very funny.
Maybe I have one around the split brain that was mentioned. Was there a solution to that? I think there was a scenario where it seems with 3-phase commit there will be a split brain.
Yes, I think I talked about it in the problems with 3PC.
Oh, okay.
I mean, there's still with network partitioning, 3PC will still lead to there's no solution to it.
Okay.
Right? It's still a challenge for 3PC.
All right, thanks.
Yeah. Yeah. 4PC. 4PC exists. Okay, so I'll start with Ugochukwu's question. He says he doesn't see the benefits, I think, of 3PC over 2PC. 3PC solves the blocking issue. Remember when we talked about the blocking issue in 2PC, we said if the coordinator fails, right, then everything is over, right? Because we have to wait for the coordinator to come back to recover or for another one to take over for it, right? However, since we have in 3PC, we have the pre-commit phase. So we have the propose phase, which if the connector fails here, then it's aborted. But in the prepare phase, the pre-commit phase, basically after the first phase where everybody says yes, if anybody gets like the pre-commit message, it means like you are going to, whether the connector fails or not, you're still going to like commit your transaction. I don't know if that makes sense, right? So whether or not, so long as we've gotten to that pre-commit phase, because in the first phase, that's the propose phase. If you say no, then everything ends. However, if we get to this phase, it means that regardless of what happens, regardless of whether the participants fail or the coordinator fails, like we are still going to commit the transaction, right? So this is where 3PC kind of shines over 2PC, right? But you can say, hey, I don't know, like in the proposed phase, what if something fails, right? This is where it looks very similar to 2PC in the proposed phase. But in the prepare phase, whether anything happens, like it's still going to be committed. Does that explain your question, Kuchku? Yes.
Yeah, sort of. But my problem is for the prepare phase is equivalent to the equivalent to the commit phase on 2PC. So in 2PC, once they get the commit message, they have to commit.
Yeah.
So I think the only major difference, like you said, is the blocking. So
Yeah.
I can see how, like Haley said, you could increase that to 4PC and 5PC and even upwards, and there would still be the problem at the end of not being sure if everything committed properly.
I need to look into 4PC because when he said it, I was thinking, oh, I thought you were serious. I thought like 4PC was actually 18. I was like, why didn't I ever see it? But okay, thank you for letting me know. Yeah, so 3PC comes with its own issues. Network partitioning, as we've talked about, that's a different issue. Performance overhead, where like it increases the overhead in terms of because of all the messaging back and forth, right? It can lead to longer transaction completion times. And also there's increased complexity. 3PC sounds great in theory, but it's not really used. Like it's not very common, right? There's also dependency on timeouts. So basically you need to set appropriate timeout values because it can lead to premature aborts or long delays in decision making. Yes. So in the book, database partitioning came after Calvin and Spanner, but I figured since we would be looking into partitioned like database systems, it's best we talk about database partitioning first. So database partitioning basically involves like dividing a database into smaller, more manageable pieces called partitions. I think we've talked about partitions in like previous chapters, right? Have we, guys? No?
Not that I remember. I know we talked about replicas. Yeah.
Okay. Okay. Yes, so basically each partition contains like a subset of the data and can be managed and accessed independently. This approach kind of improves, I said kind of, but it basically improves performance by distributing the workload across multiple nodes and yeah, increases availability by reducing the impact of failures on the entire database. There is a particular partitioning scheme known as sharding, which involves dividing the data set into smaller ranges based on a specific key, like user ID, like timestamps, etc. Each partition or range of data is managed by a set of database replicas. Like in the book, is referred to as like replica sets. And this replica set typically includes like multiple copies of the data to ensure high availability and fault tolerance. Oh, this is a lot of text. But basically, partitions are sized based on factors like load and value distribution. This involves breaking down frequently accessed or heavily read or write ranges into smaller partitions to evenly distribute the workload. So if we use like zip codes as a routing key, we have to consider that, like say in Lagos, Nigeria, populations are unevenly distributed across regions, and certain zip code ranges may contain more data, like people and others. And let's also not forget that when adding or removing nodes from the cluster, the database needs to reorganize the data to ensure balance. I would talk about some placement algorithms that databases use for database partitioning. One of the common placement algorithms is hash-based partitioning. So hash-based partitioning is an approach where a hash function is applied to the partitioning key. Like I mentioned before, it can be like user ID, product ID, timestamps, zip code, whatever, to determine the partition where the data should reside. This ensures like uniform distribution of data across partitions. The most straightforward way to map hash values to node IDs is to take a remainder of the division of the hash value by the size of the cluster. So hash key mod num partitions. However, hash-based partitioning comes with a huge con. And this, like, whenever like a large portion of data, there's going to be a lot of, how should I put it? There's going to be a lot of data movement, right? So if something happens, is the mod? It's not the same as remember. Yeah, it's like the symbol is a percentage. Yeah. Anyway, so I was trying to say that one significant, yeah, Python. Okay. One significant challenge with this approach arises when the cluster size changes, right? And it goes from n to say n+1 or n plus 5 or whatever. And this means that like a huge portion of the data will experience like altered like mappings. I don't think we have enough time for me to talk about like the pros and cons of hash-based partitioning, but yeah, let's move over to consistent hashing. Consistent hashing is used by some databases such as Cassandra, and it addresses the limitation of traditional hash-based partitioning. So basically, when a node is added or removed, in traditional based partitioning, there's going to be significant data movement, but consistent hashing kind of minimizes the need for data relocation. So in this case, when a node is added or removed, only a fraction of the keys need to be remapped to different nodes, basically reducing the overall data movement. Consistent hashing also like arranges nodes and keys on a virtual ring where each node is mapped to multiple points on the ring using a hash function. And consistent hashing aids in load balancing, so that like if a node is overloaded, then some of its keys can be like remapped to other nodes. Yeah, they do. Consistent hashing also ensure fault tolerance. it employs like replication or virtual nodes. And this is a nice diagram I saw on Geek4Geeks. Yeah, there are a couple more placement algorithms for further reading or further research. There's the range-based partitioning, there is round robin, and dynamic partitioning. We can look into it much later. Okay, so are there any questions on data partitioning or, database partitioning? That's a no. Yes, so it's time to talk about Calvin. Calvin is, I think Calvin was released in 2012. I might be wrong. I'm not quite sure about that. But yeah, 2PC has an increased contention footprints that lead to increased waiting times during commit phase. 3PC aims to reduce the blocking issues, but still faces like contention. And 2PC and 3PC face challenges in partition database systems. However, here comes Calvin to the rescue. How Calvin solves some of this problem is to schedule transactions in advance, to basically minimize contention. One of the ways it does this is to let like the replicas agree on the execution order and transaction boundaries before acquiring locks and proceeding with the execution. Calvin, like I was researching about this, and Calvin only has like FaunaDB as it, only FaunaDB actually implements Calvin. I don't know if anybody knows of other DBs, but yeah, it was mentioned in the book FaunaDB, and I looked it up, and I only saw FaunaDB, and it's not open source. So, anyway, they use. Well, not me. I will not do that. Yeah, they use a global consensus approach, like Paxos, to achieve, to basically agree on the order in which the transactions should be executed. Yeah, Calvin's architecture consists of three main components: the sequencer, the scheduler, and the storage. And this is a nice diagram. So basically what happens here is like the sequencer, you see me, oh, you don't see my cursor. Okay, so the sequencer uses like a consensus algorithm like Paxos to agree on, okay, if we're getting 5 transactions, right, this one should happen first before the other one, before the other one, before the rest, basically. And I read about it. The sequencer is the entry point for all transactions. It determines the transaction execution order and establishes a global input sequence. The sequencer collects this transaction into short time windows, which serve as replication units to avoid separate communication for each transaction. Like I said earlier, this phase uses consensus protocols like Paxos to ensure that all nodes agree on the transaction order. The next phase is the scheduler. So as soon as a transaction batch is successfully replicated, the sequencer forwards it to the scheduler. Let's go back to that diagram. Yeah, so you see after the sequencer, it goes to the scheduler. And now the scheduler uses like a deterministic scheduling protocol that executes parts of the transaction in parallel while preserving the serial execution order specified by the sequencer. Since applying transaction to a specific state is guaranteed to produce only changes specified by the transaction, and the transaction order is predetermined, replicas do not need to further communicate with the sequencer. I thought this was very important, like the knowing that transactions in Calvin has a read set and a write set. So the read set contains like the dependencies, like the set of data items that a transaction needs needs to read in order to execute like a transaction. And a write set is the set of data items that the transaction needs to modify or write during the execution. Calvin uses this set to determine potential conflicts and dependencies between transactions during the sequencing phase. And because Calvin needs to know the read and the write set in advance, it does not natively support transactions that rely on additional reads that would determine either reading or writing the set. So after it has determined the read and the write set in advance, like you cannot, maybe there are libraries or APIs that it uses to support like transactions that rely on other like additional reads. I don't know. Does anybody have an idea if it does? No. Okay. Is everybody there?
Yeah.
Okay.
Yeah, no, don't worry.
Okay.
Right here. We're just listening. Yeah.
Okay. We talked about the worker thread. So we have the sequencer, which we've talked about, the scheduler, which we've talked about, now the worker threads. So the worker thread in Calvin is managed by the scheduler and is responsible for executing the transactions as per the global sequence order determined by the sequencing phase. These worker threads analyze the transactions read and write sets. It collects the local data required to execute what do you mean? Is this like an event loop type thing?
I, I don't want to like distract from like what you're saying, but like
Yeah.
I'm struggling to like contextualize like what Calvin is, right? Like to me it sounds like an event loop, right? Like Node.js. Like it sounds like it is like a tiny version of Node.js. Does that make sense?
I mean, to me,
I think more like
yeah. Okay.
yeah. No, yeah, thread pool is good. Like different things, they put different things in different states, and other things pick them up, put them in other states, put them back in a worker queue or something, and other threads pick it. I mean that's kind of the gist I'm getting. But I don't know if there is something more.
Damila, I wanted to say something.
Yeah, that's the way I see it is the scheduler. The idea is it's trying to parallelize, like run these operations in parallel, right? Even though somehow I don't know, it's still going to make sure that everything is still in the order that the sequencer, that was gotten from the sequencer. So I just see the workers as like a thread pool where the scheduler can just schedule like the different operations that it needs to execute in parallel, and then the workers just pick them up and execute them in parallel.
Yeah, Calvin was a tough one to wrap my head around because I was like, this seems like a lot of work.
Yeah.
Like, I enjoyed reading about Spanner and researching about Spanner, which we will talk about. But like Dan Lola and Emily said, you can think about it as a thread pool. The scheduler basically, like Damnola said, like executes the transaction in parallel, and it gets the execution order from the sequencer because the sequencer is responsible for like setting the order using Paxos, right? But I don't know if that answers your question or you need to ask more.
No, that makes sense. Just go on. Thanks. Thank you.
Yeah. What was I? Yeah, I think I was saying that the worker thread one of the things it does is it collects local data required to execute the transaction. Like the read set records that like reside on that node, and then these collected data records are forwarded to the corresponding active participants. And if the worker thread is executing on an active participant node, it receives data records forwarded from other participants. That's quite confusing, even though I wrote it. Finally, like it executes a batch of transactions and persists records into local storage. Yes, we are in Spanner. Sorry, you want to say something, Emily? No? Okay.
Yeah, ask like where in the book is, I can't
You can't find Calvin?
Yeah, oh, okay, no, I found it. All right.
Okay.
I wanted to say that it kind of reminds me a lot of like a system I've worked with. That basically, so you like depending on what you want to achieve, right? You can determine like a sequence of actions that need to be performed. So I can kind of think like about like if you want to what's an example I can come up with? Like there's a task that needs to go through like a particular sequence of actions, like whatever it is, right? You kind of define it with your sequencer, and when like so there'll kind of be something that triggers it, right? So you know that this sequence of actions needs to be performed, and then it is triggered, and then it is scheduled. So some of those tasks might be run at different times with different cadences, right? In the real world, maybe you want to like roll out, if something is like code is going through rollout stages, it kind of maybe goes slower in some instances, faster in others, like just depending on how you schedule it. And then workers would be the things that, for example, make all the API calls you need to make, you know, get data from the local, get data from remote, mix them together, perform logic, do what you want. And then you kind of need to store the state. So after the operations are done, you know, you need to store the state so that it's persisted. You know, other systems can use that information for other things. So that's kind of my understanding. I mean, I know we're going into a lot of detail about what each thing is doing, but that's kind of high level understanding that I'm going away with, right? So yeah, just wanted to communicate in case it helps someone.
Thank you. Spanner. So personally, I'm biased towards Spanner, and I think it's because it utilizes things like physical clocks, which we will talk about, 2PC, which we've talked about, and Paxos, which we've somehow talked about today. Spanner was created by Google, and it provides both linearizability and serializability. Yeah, so like I said before, it uses stuff like TrueTime API, which was also created by Google. 2PC, Paxos, Pashad to manage distributed transactions, ensuring strong consistency and high availability across the globe. Spanner uses Paxos for consistent transaction log replication, two-phase commit for cross-shard transactions, and TrueTime for deterministic transaction ordering. Remember earlier, yeah, TrueTime API. Remember earlier when we said Calvin uses Paxos, but it was on a global level, like in the sequencer, right, to determine the order in which the transactions should be executed. However, with Spanner, like it uses Paxos on a shard level. So it's not global, basically. Google Spanner typically incur higher costs and latencies due to the additional coordination required for two-phase commit across multiple partitions. Oh, that was too fast. So because we've talked about two-phase commit and Paxos, I think we should talk about true-time API for a few minutes. So yeah, like I said before, developed by Google, it uses atomic clocks and GPS to provide precise timekeeping. Just to be clear, have we talked about clocks in the previous chapters? We have.
Yeah, there was a whole thing about like Lamport clocks and vector clocks and
Yes. So if we recall, atomic clocks are actually physical clocks, right? And you might be thinking, Lamport clocks are actually better here, right? We shouldn't like try to rely on physical clocks because we would experience clock drift or clock skews, right? But the thing is, if you remember, Lamport clocks actually they do not have like a physical clock, like the essence of a physical clock. When a transaction is sent from one node to the other, the particular node takes the timestamp of the message and then calculates, like, uses the max of the timestamp of the message and its own time. That's how it calculates time, basically. So, and that would not work with true time, with Spanner rather, because with Spanner doesn't really communicate with other nodes. Like that might not happen. So you actually want to use a physical clock. So yeah, true time API basically like accounts for clock drifts by returning a time interval. So there's T earliest and there's T latest. T latest basically is like the clock drifts, like an estimated clock drift, and that way we have we have to wait. Basically, like when a commit request is made, Spanner must wait until like this time interval has passed. It has to wait until T latest has passed until that's when it now commits the request. I don't know if that makes sense. But I have a nice diagram that I took from Martin Klepman's video. So basically, you see node A and node B. So there's T1, which is transaction 1, right? So it makes a commit request, and you see the T1, that's the time 1 because it's a small letter, earliest, and then the later. So the wait time before the commit is done is literally like the time between T1 and T latest. So T latest has to, like, as I don't know how to put it, but has to have been exceeded before the commit is like actually done, finished. And this also helps because if you look at T2, there is no overlap between T1 and T2. That's literally why we have to wait. Like calculate the true time does this for us, but calculates the what's English? Calculates the clock drift, and then use it to let it be the T1 latest, basically. I don't know if I've made sense or I was just rambling. So if you have questions, please ask me.
So it sounds like the reason for this clock, I mean, when we looked at the logical clocks, I think that was also part of the reason is to establish some form of order using I mean, we can't use the physical time with logical clocks, but using time in a way to establish order. And that's what we are doing in this case. But now Spanner is using a physical clock to call true time to actually achieve this ordering. Okay.
Yeah. Was that your question? Sorry.
No, just like to confirm like that's what's happening here. Even
Yes.
I think the only question I was about, I guess I'll have to research it is, how does this work? Like, yeah, how come somehow Google is able to figure using physical clocks when when it looked like it wasn't feasible, and then we had to come up with like logical clocks. Yeah.
Yeah, I mean, they just thought about the problems with physical clocks, right? There are two types of physical clocks. There's the quartz, is that how it's pronounced? Quartz clocks, and the atomic clocks. And atomic clocks actually provide the highest level of precision, right? So they use atomic clocks and GPS, what do you call GPS systems, right? And they were like, oh, so the problem with atomic clocks is clock drift can happen, right? So how can we account for this clock drift? So basically so that there's no overlap, because we want to establish some sort of causality, T1 happened before T2. So it means that T1, like we shouldn't see like the timestamp for T1 less than or greater than T2 rather. I don't know if that makes sense, right? So they were like, oh, so if the commit request was made at 8 o'clock, then we should have, based on what we've seen, based on the assumptions we've made, right? Say there is a clock drift of 6 milliseconds. So let's wait for 6 milliseconds before we can commit this transaction.
Okay.
Do you understand? Yeah. I would link the videos that I found about true time to Discord, and we can have like more conversation in the channel. Sorry, this is a side note. Should I keep going because we are past 9 o'clock or 8 o'clock your time, or this is to Damilola because you're the host?
Oh, yeah, I have to pass it. I'm fine. I would like to. I think Spanner was the main one I was really interested in, especially the tablets and like how it works. So maybe when we cover that, I'm fine. But I can.
So you can drop if after we're done with one.
I think that's the last one, right? Okay, there's Percolator. Okay. Yeah. But I think since we're already talking about Spanner, maybe we can just wrap it up, and then wherever, yeah, we can end it from there.
Okay. Yeah, so Spanner offers like 3 main operation types: the read-write transactions, the read-only transaction, and snapshot reads. Right. So read-write transactions like requires, as you can imagine, they require locks, right? And they occur in the leader replica. However, read-only transactions are lock-free and can be executed at any replica. Snapshot reads basically provide like a historized view at a particular timestamp. This allows snapshot reads to be performed without interfering with other transactions. And I think it was mentioned in the book that because like after you make a write, I don't know if I'm getting this right, somebody please correct me if I'm wrong. If you make a write, like order or a read at a particular time, the other previous transactions are not deleted. Is that right? I think I am, so I'm just going to leave it at that. But if you think I'm wrong, because I'm not quite sure about that, let me know. Yeah, remember I said earlier that for read-only transactions and snapshots reads, the leader is not like needed. You can actually do both of those things on the replica. However, if you're trying to read at the latest timestamp, you need to read from the leader. Like the leader is actually required for reads at the latest timestamp, basically. And this is an equally nice diagram. Yeah, bye, Ayo. So this is a nice diagram showing the architecture of Spanner. Yeah, so I basically just wrote like what happens, like what happens on the leader, the group leader, how two pieces executed, the transaction manager, log table, the role of Paxos, tablet in the storage. So I said every write has to go through the Paxos group leader, while reads can be served directly from the tablet on up-to-date replicas. The leader holds a lock table that is used to implement concurrency control using two-phase locking mechanism. And the transaction manager is responsible for multi-shard distributed transactions. Operations that require synchronization, like write and read within a transaction, have to acquire locks from the lock table, while other operations like snapshot reads, remember I said it's just read at a particular timestamp, can access the data directly. For multi-shard transactions, the group leaders have to coordinate and perform two-phase commits to ensure consistency and use two-phase locking to ensure isolation. Since the 2PC algorithm or protocol rather requires the presence of all the participants for a successful commit, this hurts availability just in case one of the participants is down. But Spanner solves this by using like Paxos groups. This is what Ugochukwu talked about earlier. So this means that 2PC can continue operating even if some of the members of the group are down, because yeah, they just need to, it's like a quorum, right? So within the Paxos group, 2PC contacts only the node that serves as a leader. Spanner is implemented in open source DB such as CockroachDB and Yugabyte DB. I would also link articles that I found from Yugabyte DB, talking about the differences between Spanner and Calvin, Spanner and Percolator. I think that would help us with our research. So we said we're going to stop here. Maybe I should move to the conclusion. Yeah. So
Sorry, I think if we can like take 5 minutes to talk about coordination avoidance.
oh yeah. Do you want to talk about it?
Oh, I thought it was like on what you wrote up because I was finding it a bit confusing understanding some things about it. But from what I understand, basically it tries to avoid coordination like the name implies, having to, use 2PC to wait for a transaction, for a message or a transaction to be complete and all that stuff. Basically, all the things we've discussed about by being able to look at in-flight operations. So if there is a concurrent transaction happening in a shard which you need information from to read, let's say for example, you want to add X and Y, and to add X and Y, you have to read both X and Y, and X and Y are in two different shards. And then you try to read X, but there is also another in-flight operation to update X. So X is currently 50, Y is 50, I'm just assuming. And then there's an in-flight operation to update X to 70. So what's the second transaction which is trying to add it? Assuming the update transaction is the first transaction, what the second transaction which is trying to add it would do would be to check the first transaction. You will be able to see that there is another transaction trying to update this, and then to be able to get that number from the transaction's metadata and know that the current value is 70, and then it's make an addition, and that would be 120. So, but one of the things I was really confused about is what happens if that in-flight transaction fails. So I was trying to figure that out with some research, and I found someone saying it wasn't an official thing. It wasn't written officially anyway. That's why I wanted us to discuss about it. I was hoping someone had some insight. Is that actually the second transaction doesn't complete until the first transaction is done. So in our case where we had 7C updating it, the the second transaction, which is T2, which does the addition, would actually have to get info and maybe wait like an event emitter design pattern, and then you have to actually wait for the first transaction to be done before it can relay the results of its own transaction. And I felt like even if that happens, even if that solves the problem, it's still going to cause some delay because we are not really solving the problem. We're just creating a new problem and removing another one. So
Yeah.
that's just my understanding about it and what I was hoping to ask.
Yeah, and that was also a bit confusing for me because like I was reading about it and I saw like ramp transactions, that's the read atomic multi-partition. And I read that it also like uses like 2PC. And I was like, it feels like we're not solving the 2P because we already originally like talked about how 2PC has a lot of problems, right? And people just keep building on 2PC, right? And it was also quite confusing to me that like just like you said, the whole how ramp allows like multiple versions of basically the same record to be present at any given moment, like in-flight uncommitted changes, still versions, blah, 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 blah. Yeah, it was quite confusing. Maybe we can actually have like a conversation another day. Yes.
Sorry, just to chip this in, two-phase and like distributed locks are not super like used like generally. Like there are a few like implementations, right, in like some databases, but in terms of doing, there's other ways of solving the problem in general. Like this is more like for your own like learning or knowledge, mostly. Yeah, people typically try to avoid using these kinds of like convoluted like locking schemes. Is my opinion, you know.
Wait, are you saying that 2PC is not used here, like in ramp?
Oh no, that's not what I'm saying. Like I'm just saying like generally, right? Like in software development, right? Like if you're trying to like do stuff, right? You wouldn't necessarily reach for 2PC as like your first go-to thing, right? Because people, I think this was mentioned in like a previous like session, like people typically like use sagas and stuff like that, right? Like people try to work around like I guess this space because there's no like perfect solution for like there's no off-the-shelf like solution for like distributed locks, like right? Like it's still like an unsolved like thing.
Yeah, but like I get what you mean. However, because I was going to put sagas as a like another way for us to like achieve distributed transactions. I don't know if achieve is the right word. However, like sagas are very specific to like long running transactions, right? Sagas are very specific to because you would not want to use for a very simple transaction that is not really long running. You wouldn't want to use sagas. Well, like you said, like nothing is perfect. Everything has like pros and cons, and yeah, but it was quite baffling that like we're talking about like coordination avoidance, and the solution they provided used 2PC. Spanner uses 2PC. Percolator also uses 2PC. So I'm like, why am I seeing 2PC everywhere when we've all agreed that 2PC is a problem, right? But yeah, we would have this conversation. Yeah, I'm happy to like talk about at a later time. Talk about this coordination avoidance. Maybe we can like go research and come back and basically have a real conversation about it. But yeah, to conclude, Yeah, we said TPC is a common protocol used to achieve atomic commits. We said it's easier to implement. However, its major downside is that it enables blocking. TPC is not commonly used, but it solves the major limitation of TPC, but it's prone to split brain in case of network partition. We talked about how many DBs use partitioning to divide data into smaller manageable segments. How regular hash-based partitioning can cause significant data movement when nodes are added or removed and the cluster size changes. We also touched on consistent hashing, how it minimizes the need for data relocation and provides a more scalable and fault-tolerant approach to data partitioning. We talked about how Calvin uses a sequencer which determines the order in which the transactions are executed, and a scheduler which orchestrates transaction execution. We talked about how Calvin uses Paxos to reach consensus on exactly which transactions make it into the current batch. We also talked about TrueTime API, which Spanner utilizes alongside Paxos and TPC to achieve globally distributed transactions with strong consistency and high availability. We did not talk about Percolator, but Percolator employs a timestamp ordering mechanism and distributed locking to manage transactions over large-scale data sets, and it provides strong consistency and fault tolerance, making it suitable for real-time data processing workflows. And that is the end of distributed transactions. Thank you. I know it's pretty late, but if you have any questions, please just say it on the Discord channel. And if I don't know the answer, I will either go research or we can have a conversation about it. Thank you so much for your time and for listening to me ramble.
Yeah, thanks a lot, Chidinma. And thanks everyone for joining. Yeah, have a nice day.
Yeah. Follow me on Twitter. Bye.